Hello and welcome to Tech Simplified TV. A state-of-art IC contains billions of transistors. Placing each of them in a limited space and connecting each of them with power and ground is a huge task. If we divide a complex circuit in smaller modules and handle each module separately, that might help us. Yes, we do exactly that. In VLSI flow, we call it partitioning. And in today's episode, we will discuss about different aspects of partitioning. So if you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and partitioning. Next, more on partitioning, level of partitioning. After that, why partitioning is important. Next, rules of partitioning, graph theory and partitioning, pin and net oriented netlist, partitioning algorithm. There is another slide on same topic, that is partitioning algorithm. So these are the pointers we will cover in today's episode. We are done with this slide. We will move to the next slide. Design flow and partitioning. This is the VLSI design flow that starts from system specification, then architectural design, functional and logic design, circuit design, and here front end ends. Now physical design, that is basically back end, and physical design is not a single step. There are multiple steps like partitioning, chip planning, placement, clock tree synthesis, signal routing, timing closure. Once everything is done satisfactorily, then that moves to physical verification and sign off, and after that fabrication and packaging and testing, and finally the physical chip come to customer's hand. So VLSI design cycle is broadly categorized into front end and back end. We know that front end starts with system specification and FE defines the logical behavior according to the functional specification. At the end of the front end, we get technology mapped gate level netlist. So this is the objective of front end. Now backend starts from there, and main focus of backend is to translate the circuit we have got in front end into silicon wafer with proper placement of blocks, essential power lines, routing, and etc. After all these steps, the process lead to tape out. So this is a small description of the flow. Now partitioning is initial step in physical design process. Partitioning is dividing a chip into smaller blocks. As the name suggests, now different functional blocks are separated and routing placement is simplified. The designer breaks the larger design into various smaller functional modules or blocks and then proceeds with implementation of these smaller modules during RTL design phase. These smaller functional blocks are structurally linked in the main module. Main module is called top level module. This type of partitioning is called as logical partitioning. So there is a top level module and there are some other modules also. The total design, a bigger and complex design that is divided into smaller blocks and they are handled separately. That is the main theme and purpose of partitioning. We are done with this slide. We will move to the next slide. So more on partitioning. To simplify complex integrated circuit design, they are divided into smaller parts called modules. These modules can be simple as few electrical components or as complex as fully functional integrated circuit. If the total design is doing multiple work and very complex work, when we subdivide the total circuit into smaller parts, so one part is as good as a functional IC. A tool called partitioner splits the circuit into smaller sub-circuits, partitions or blocks. It aims to reduce the number of connections between these partitions while adhering to design rules like maximum size and delay limits. So partitioning might help us. Also, we have to consider some other constraints like design rules, allowable maximum size and delay limits. We cannot ignore them. There is an example circuit with 8 gates and we can cut it or divide it into two different ways. Like this is cut 1. If that is the cut 1 in one section A, B, C, D, these 4 gates in block A and E, F, G, H, these 4 gates in block B. So we are following same connection, keeping the connection same, that is functionality same. So interconnect between these two blocks is 2. Now, if we divide the circuit in different way, like A, B, D, E comes in one block and C, F, G, H comes in another block, keeping the same functionality, number of interconnects here become 4. So, how we arrange the gates depending on their functionality, interconnection between them, number of interconnections depend on that. Now, if each block is designed without considering the others, it can lead to problems. Since both the blocks are part of a big design, so we have to consider others also while designing one. More connections between partitions can increase circuit delay and decrease reliability. We know interconnection reliability issues related interconnections are there. Airdrop will be more. So too many connections can create dependencies that slow down the design process. The main objective is to minimize connections between subcircuits to improve performance and meet design constraints. That is the main objective. So constraint may include limit on logic size in a partition or number of external connections that is limited by the number of I/O pins on a chip. Now, by following these points, designer aim to create efficient, reliable, and easily manageable integrated circuits. A designer has to follow all these constraints. So we are done with this slide. We will move to the next slide. Next is level of partitioning. Now, circuit partitioning is an important task in VLSI design application. Partitioning algorithms are used to achieve various objectives such as circuit layout, circuit packaging, and circuit simulation. Partitioning can happen at 3 levels: system level, board level, and chip level. There is an infographic. At system level, if we do partitioning, we lead to some PCBs, multiple PCBs. On a single PCB, if we do board level partitioning, we lead to some multiple chips. And at chip level, if we do partitioning, we end up with subcircuit or block. So, system level partitioning, a system is partitioned into group of PCBs. Each subsystem can be designed as single PCB. Board level partitioning, a PCB is partitioned into subcircuit, each subcircuit fabricated as VLSI chips. And third, chip level partitioning, circuit assigned to chip is divided into manageable subcircuits. So this is all about level of partitioning. Now we are done with this slide. We will move to the next slide. Why partitioning is important? This is the main theme of partitioning. This is the system now break into multiple modules. Physical packaging. Partitioning decomposes the system in order to satisfy the physical packaging constraint. The partitioning conforms to a physical hierarchy ranging from cabinets, cases, boards, chips to modular blocks. Divide and conquer strategy. Partitioning helps manage complex designs by breaking them into smaller parts. This approach allows team members to work on different sections, creates a logical order for design, converts the netlist into a physical layout for planning, assigns cells to specific areas for placement and RLC extraction, and coordinates between logic and layout for simulation. So divide and conquer strategy, a big complex system, divide and different team member can work on different sections. So that actually is the process. Now system emulation and rapid prototyping. On one way to test a system is by using FPGA to create the hardware. Now since FPGA often have less space than modern VLSI design, this prototype system use several FPGA arranged in hierarchy. A partitioning tool is needed to fit the netlist onto the hardware. By partitioning, we are reducing the whole system into smaller parts, and FPGA often have less space, so hierarchically we can use FPGAs, arrange them and fit the netlist into those. Partitioning tool can contribute here. It is needed to fit the netlist into the hardware. Now hardware and software co-design. For hardware and software co-design, partitioning is used to decompose the design into hardware and software. Management of design reuse. For huge designs, especially system on chip, we have to manage design reuse. Partitioning can identify clusters of netlist and construct functional modules out of the cluster. Part of a design can be reused. That actually saves time and money. In that case also, partitioning helps. This block diagram we have already used in our previous slide. Here also we have used it just to show how partitioning breaks a bigger module into smaller modules. So we are done with this slide. We will move to the next slide. Now rules of partition. We can do partitioning, but there should be a constraint. There are some rules we have to follow. There are some points we need to take care, like interconnections between partitioning. Reducing interconnection decreases delay and interaction between partitions, simplifying independent design and fabrication. So interconnection between partitioning, we have to keep that is less, because more interconnects means more delay and more reliability issues. Partitioning a circuit may result in the critical path crossing between partitions multiple times. That might increase the delay. Number of terminals, the number of net needed to connect a subcircuit to other subcircuit does not exceed the subcircuit's terminal count. That's a constraint. Now, number of partitions, a large number of partitions can simplify the design of individual sections, but it may also increase fabrication cost and the number of interconnections between partitions. Another thing is area of each partition. There is a spelling mistake. There should be 1A, area of each partition. Area of each partition is also a very crucial point, because the whole area of core is determined by the floor planning. Floor planning give you the total area. Within that, we have to fit all the partitions, and how those partitions are arranged, how those blocks are arranged. That is another part of floor planning. But the constraint is there. Total area constraint is there. Delay constraint is there. How many interconnect, that constraint is also there. So area is another point, because power performance area constraint is always there. That factor we cannot ignore. So these are the rules we have to follow. And there is a diagram. So there is one PCB, there is another PCB, PCB1 and PCB2. There are two chips where there are two modules, A, B, and another chip, that is, there is a module C. So this A module of this chip 1 is communicating with B, that time is X. When it's communicating within same PCB another chip, time increases 10x. If it's communicating with D, C to D, that is 20x. Now, if we bring that module within that chip where C is there in another design, so overall that communication time between C and D reduces. So how we place the module depending on their connectivity, depending on their connections and function, how frequently they need to communicate with each other. We have to keep it all in mind. So that way partitioning can be done. It's not that randomly we do it. No, obviously not. Depending on the functioning and depending on interconnections, and because longer interconnection means a lot of time is there required. So we have to take care all of these things. Now, what happens after circuit partitioning, or what we get after circuit partitioning? Area occupied by each partition is estimated. Now, possible shapes of blocks can be ascertained. Number of terminals required by each block, that is also known, and netlist specifying connections between block is available. So these things we have, and from there we will move to floor planning. So we are done with this slide. We will move to the next slide. Now, graph theory and partitioning. Graph theory is the core thing behind partitioning. Whenever we are taking example of smaller circuit with 7-8 gates. Now think, when number of gates thousands or in millions, how will we, with the complex connectivity and complex functioning, how will we do that? That's a real tough thing to do. So there comes utility of mathematical models, that is behind all the commercial tools, popular tools. They use those mathematical models behind them and do it. There comes the importance of computation. Now, graph theory is the basic of partitioning. So graphs are used in physical design algorithm to describe and represent layout topologies. A graph is G, function of V and E, is made up of two sets, elements and edges. Set of nodes or vertices denoted as V, and relations between elements denoted as E. So this is a simple graph. These are vertices and their connections edges. So elements and edges. Now this is hypergraph. A hypergraph consists of nodes and hyperedges. So these are nodes and these are hyperedges. In a graph, an edge is connected with two node or two vertices. In case of hypergraph, multiple node can be connected. In a hypergraph, edges are set of any number of vertices, not restricted to number 2. Hyperedges are commonly used to represent multi-pin nets or multi-point connections within circuits. So basically, In practical, our circuits are also multi-pin and multi-point connections. So hyper-edge is suitable to represent them. Here we can see there is one hyper-edge E2 consisting these two nodes 1 and 2, E1, 1 and 3, E4 is with 1, 2, 3 and 5, and E3 is with 2, 3, 4. These are hyper-edges. So this is graph, this is hypergraph. Now there is a circuit, simple circuit with 7 gates, and if we represent that circuit with the graph, that is this way, and hypergraph this way. Now notice this point, how it's different. C, E and G. E and G both are connected to C. So if we represent with graph, because in graph, two nodes can be connected, C to E is connected and E to G is connected. This way. And hypergraph, multiple nodes can be connected. So C to E and G this way connected. This is the difference between graph and hypergraph. So order of hypergraph, size of vertex set, and size of hypergraph, size of the edges set. This is the definition of order and size of hypergraph. So we are done with this slide. This is very basic of graph theory, and with a small circuit, a very small circuit, we just try to represent how it can be represented for understanding only. Now we will move to our next slide. Now pin and net oriented netlist. Everything we are doing, we actually do this partitioning on netlist. So a netlist is a list that shows all the connections on nets and the components they link together in a design. It can be organized in two ways, pin oriented and net oriented. This is the circuit, this is net oriented description, this is pin oriented description. Netlists are created during logic synthesis and are a key input to physical design. We already have a series on synthesis and EOSIS. Watch it for better understanding. Now, a connectivity graph is representation of netlist as a graph. Cells, blocks, and pads corresponds to nodes, while their connections correspond to edges. So, we have presented it as a graph also. So, in net 1, net 2, net 3, net 4, net 5, their descriptions. From this description, we can understand the circuit. This is gate X. Net 1 is connected with input 1 and Y input 1. Net 2 is connected with input 2 of X and input 2 of Y. This way, description is done. Now, a net 3 is connected with X, output of X and input 1 of Z. This way, connection is done. So, this is the graphical representation of this circuit. So, this way, pin and netlist can be represented in pin and net oriented way, and we can represent it in graph also. So, now we are done with this slide. We will move to the next slide. Partitioning algorithms. A cell is any logical or functional unit built from components. A partition or block is grouped collection of components or cells. The components are there, and a group collection of components and cells that makes a partition or a block. The K-way partitioning problem seeks to divide a circuit into K partition. The most common partitioning objective is to minimize the number or total weight of cut edges while balancing the sizes of the partitions. Often partition area is limited due to packing considerations and other boundary conditions implied by system hierarchy, chip size, or floor plan restrictions. Because of that, now circuit partitioning is very hard to solve. As the problem gets bigger, the time needed to find the best solution grows very quickly. There is no known fast and perfect method to solve balance constraint partitioning. There are two types of partitioning methods, constructive and iterative method. A constructive algorithm creates a partitioning from graph that represents the circuit or system. Iterative method works to improve the quality of an already existing partition or solution. And deterministic or probabilistic method, deterministic program always produce the same solution each time they run. Probabilistic method give different solution each time because they use random numbers. So these are the types of partitioning, and these methodologies are all required methodologies are all within the tools. There is a small example. There is one block, another block. There are 4 nodes, and if we consider the interconnections between them, so there are 9 interconnections between these 2 blocks. And if we rearrange, keeping the functionality same, the connection become 1. So from cut size 9 to cut size 1, that is reducing. We are done with this slide. We will move to the next slide. Partitioning algorithm. This is the second slide on the topic. Now, There are methods which are followed, like methods like Cunning and Lean or KL algorithm and fiducium matrices or FM algorithm can find good solutions and run relatively quickly. Optimization using simulated annealing can address particularly challenging partitioning problems. KL algorithm is sensitive to the number of nodes and edges. KL algorithm performs partitioning through iterative improvement steps. It's based on exchanging or swapping pairs of nodes, each node from a different partition. FM algorithm is sensitive to number of nodes and nets hyperedges. The FM algorithm is typically applied to large circuit netlist. The algorithm is more naturally applicable to partitions of unequal size or presence of initially fixed cells. FM algorithm offers best trade-off between solution quality and runtime. Now, partition area is limited by packing considerations and other boundary conditions such as chip size, floor plan restrictions. We have repeated this point because we have to always remember whatever may be the algorithm or methodology, we have to be restricted by some constraint like chip size, floor plan, etc. And we have to work within that, keeping cost as low as possible because everything is for business and high cost is not viable for business. Now, let's see what commercial tool contributes here. Now, commercial tool uses command line options or GUI to create manage partitions. So, we're using usually command line. Most of the commercial tools, either they have command line options or they run on GUI. Changes the netlist tree structure to create hierarchy nodes at the top level that can be physically divided. This ensures that the nodes are evenly sized and reduces the number of top level connections needed for hierarchy blocks. So whatever needed, tools does that. They have that algorithm inside them, finds the best way to divide design into blocks that can be worked on separately, makes sure the partitions are balanced by size or number of instances, reduce the number of top-level connections between block I/O ports, ensure the netlist is partitioned without changing how it works. We are understanding all these things with small example, and R&D engineers in commercial tool vendor companies, they are putting all these tough algorithms inside the programming. It requires a lot of human effort, human time. That's why commercial tools are so expensive, does so complicated work. We are trying to understand it, although we don't have to do it by hand because billions of gates can only be handled by computation. There is no other ways. So we are done with this slide and we are done with our today's episode. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have a dislike, please put it as a comment. Your question and queries are welcomed. Please put it as comments. Thank you again and bye for today.